Here are the solutions for the Scholar End of Topic 6 test. In the first question, question 15, we're asked for the EMF, so that's minus L di by dt. Pop in the values from the question and we get negative 8.25 volts. The negative indicates that this is a back EMF. The question, however, asked only for the magnitude, which is why the question says don't include the negative sign in your answer. 8.25 volts. Question 16, we're asked for the energy stored in the inductor, so that's half Li squared. Again, pop in the values from the question and you should get 0.48 joules. Question 17 asks for which of the following is exactly equal to 1 Henry, Henry being the unit of inductance. And by definition it is 1 volt second per amp, so the answer you should pick for that one is C. Question 18, the first question that requires a bit of deeper thinking. In order to get the EMF, which we're asked for, we need to get the rate of change of current. In order to get the rate of change of current, we need to realise that the values they give us for the changing resistance in the question is what's going to allow us to use the battery voltage, because remember it says there's no internal resistance, and the initial and final values of resistance to calculate an initial and final current. And then we can simply do final current minus initial current divided by the time it takes for the current to change, which is also given to us in the question. And that should give us this value for the rate of change of current measured in amps per second. And then we're able to use that with the inductance we're given in the question to work out the EMF. In question 19, we're asked to work out the EMF of the supply, but we're not given the usual information for it. So what we need to do is take the energy that's stored in the inductor, which we are given, and the value of inductance that we're given, and use that to work out the steady state current. And then once we know the steady state current and the resistance in the circuit, which we're given, we can then work out the EMF of the circuit. So E equals a half Li squared, rearrange and solve for I based on the values given. Then use I times the resistance to get our EMF. Now, notice E for energy, E for EMF. Don't get them muddled up if at all possible. Number 20, we're asked for the voltmeter reading. And this is where people can get themselves tied in a knot. So, we work out the back EMF due to the inductor, minus L di by dt, negative 1.7 times 2.1, negative 3.57 volts. The voltmeter reading, what the voltmeter will read is the supply voltage, which is 12 volts according to the question, plus any EMF in the circuit, any other electromotive force. The voltmeter will read the total of the potential differences across whichever point in the circuit that you have connected the voltmeter. So it is 12 plus negative 3.57. It is not 12 minus 3.57. So this bit here, where I'm saying the supply voltage plus the back EMF, is the bit where I show my understanding of the physics. Then it's 12 plus negative 3.57 to give me 8.43 volts. Question 21. It'll be 2.6 volts, assuming there's no internal resistance. Part 2, it'll be 0 volts. And part 3, current, voltage over resistance, 2.6 over 14.19 amps. Question 22. And again, this one requires a bit of thinking, but they've conveniently broken it down into pieces for you. So part 1, calculate the magnitude of the back EMF. So EMF formula, minus L di by dt, negative 0.34 times 1.9, value supplied in the question, gives you a back EMF of 0.65 volts. So the EMF is negative 0.65 volts. The negative sign tells us it's a back EMF, so magnitude of back EMF 0.65 volts. Given in the question, we have a supply of 1.5 volts and a resistance of 35 ohms. So what's the maximum current? It's 0.043 amps. Current equals voltage over resistance for the maximum current. And then the energy stored in the inductor at the steady state current, which is of course the same as the maximum current, is a half Li squared, half times 0.34, which we're given in the question and we used up here, times the 0.043, which was the current we got in part 2. Remember to square it, and you should end up with 3.1 times 10 to the minus 4 joules. 23 and 24 also conveniently broken up into sections for you. So 23 part 1, what's the EMF? Minus L di by dt yet again. We're told the EMF was 7. What is the inductance? If the di by dt is 60 amps per second, so L equals 7 over 60 equals 0.12 henries. There is it. So to find the inductance, EMF divided by the rate of change of current. You'll notice that a minus sign has gone walkies in here. We get away with that arithmetically speaking because remember that minus sign is there to indicate that this is a back EMF, not an EMF. So yes, we should really have a minus sign in there. But since we don't have such a thing as a negative value of henries, we can deduce that the rate of change of current must have been a negative value. So let's just tuck that in there just now. It must have gone down by 60 amps per second instead of up by 60 amps per second. Number 2, or rather part 2 of 23, I equals V over R, 7 volts over 40 ohms, 0.18 amps, and then part 3, energy stored, half Li squared again, a half times the inductance, which we got from part 1, times the current squared, which we got from part 2, and that should give us 0.02 joules as our answer. And then finally number 24, part 1, 2.8 volts, part 2, 2.8 volts, part 3. Why have I done I equals V over R here? Well, it's so that I can do this substitution here. And why am I doing this substitution here? It's so that I can have a moan about intermediate rounding. So I've taken my energy formula, E equals a half Li squared. I've substituted in V over R for I, which gives me E equals a half L V squared over R squared. And then I've put in the values from the question, a half times 0.32 times 2.8 squared over 16 squared. And that should give you 4.9 times 10 to the minus 3 joules. And here is where it gets interesting. If you were to work out the current over here and then substitute a numerical value in for the current here, I am willing to bet a curly whirly that your rounding of the value here and then substituting in here would give you a slightly yet importantly different answer. And that's what's known as the curse of intermediate rounding, and I would strongly encourage you to avoid doing it at Advanced Higher Physics because the markers are on the lookout for it, and if they see intermediate rounding that is incorrect here, then all of this will automatically get 0 because of the incorrect rounding, the intermediate rounding. So try to avoid intermediate rounding whenever possible.